12 chemists, welcome to TP's Chemistry Cuts. In this second video about Le Chatelier's principle, we look at the effect of changing temperature on chemical reactions at equilibrium. We go on to predict the effect of temperature changes on the value of Kc, and then finish the video off by looking at the effect of catalysts on equilibrium systems.
You notice I've only said concentration and pressure do not cause Kc to change. This does. So this is a little bit more involved. Okay. Now, there's a bit about heat and chemical reactions that you won't know about, that you need to know about before you can actually interpret what actually happens when you heat or you increase or decrease temperature. And that is that there are two types of reaction in terms of energy. There are those reactions that you add things together and they get warm or hot in some cases. So, for example, if you add concentrated sulfuric acid to water, you can cause the water to boil because there's so much energy given out. Okay, so those are what we call exothermic reactions. Okay, exo for given out, and thermic because it's heat, so it's heat given out. Okay, so exothermic reactions are ones that give out heat energy, and generally they get hot or warm. And there are some reactions where you carry out the reactions and it gets cold. They actually feel cold, and when they feel cold because they're absorbing heat energy, and those are what we call endothermic reactions. Now, the reasons for why some reactions are giving out heat energy and some are absorbing them, we will cover later in a different standard. But for the moment, you just need to know that those two types of reactions. Exothermic reactions give out heat and get warm, whereas endothermic reactions absorb heat, so they actually get cold because they absorb heat from you. Okay? So let's write that down. Now, I've just added an extra thing there, where I've put that funny looking symbol there. And that's a triangle, which means delta. It's delta, capital Greek letter delta, and it means change, changing. And so that's a change in heat energy. Okay? It's all change in enthalpy, and we'll deal with that later. One of the ways of working out whether you've got an exothermic, or the way of working out whether it's an exothermic or endothermic value, is these are usually quoted along with the reaction. So if you see this with a negative value put beside it, then that tells you it's exothermic. Okay, that's all you need to know for the moment. So you just look for that symbol, and if it's negative, the number that expired, exothermic reaction. So it's a way of identifying it. If you look at endothermic, it's the opposite. So those are the important bits. Exothermic give out energy, heat energy, negative delta H. Endothermic absorb, positive delta H. So let's look at an example of a system at equilibrium. Okay? And we're going to link in the type of reaction. So we've got our forward reaction. Our reverse. And generally, what often happens is you get, and let's say it's a negative number here. The problem is we've got two reactions here, the forward and the reverse. Which one does that apply to? And the answer is quite straightforward. By convention, we always put the value here that relates to the forward reaction. So anything here relates to the forward reaction only. So the reverse reaction is just the opposite of it. So if it's, say, minus 100, it would be plus 100 for reverse. Okay, so they're exactly compatible. Okay, so we'll put that down. So in other words, if you see something like this, get yourself a pencil and then put in the forward reaction and put exothermic. So in this particular example, the forward reaction is exothermic and the reverse reaction is endothermic. Don't assume it's always going to be like that. It depends on what people think of as the important reaction, because you can always swap this over. Okay, so it might be that we're doing a critical reaction as part of the process, and the forward reaction just happens to be endothermic. Okay? So you don't sort of nicely swap it over just because by convention it's always exothermic going forwards. That's not the case. It can be either way. So let's continue with this one, because we're going to sort of lead on to a system that will make it easy to apply Le Chatelier's principle. Okay. So what we're saying is that this is an exothermic reaction going in the forwards direction. So in other words, when A plus B react together, they form C and they give out heat at the same time. Energy is given out. So you could effectively say that heat itself, heat energy, is a product, because that's what's formed in the reaction. Yeah, you're giving it out, so it's a product. Yeah? So we could actually write this slightly differently. Okay? So we could write this as A plus B C, and I'm going to put it in green, plus delta H. So in other words, A plus B react together to form C and some heat. Yeah? And then C takes in some heat and then forms A and B in the reverse reaction. Is that okay? Don't ever write this. This is just to try and give you some idea as to what happens when we apply Le Chatelier's principle by increasing the temperature or decreasing the temperature. Okay? So, have I confused anybody by doing this? So long as you understand it's an exothermic reaction, because I've looked at this value here, it's negative, it's telling me the forward reaction is exothermic. So whichever direction is the exothermic reaction, the product of that reaction is going to be, one of the products is going to be heat. And I'm just going to write it like that. Now, we can apply Le Chatelier's principle. So say, do you want to heat or cool down? You want to cool down because you want to be chill. Okay, so we're going to cool down. If we cool something down, what are we doing in terms of heat energy?
Losing.
You're losing it. You're removing it, aren't you? So in other words, you're taking away some of that. Yeah? By cooling it down, you're removing some of the heat energy. So what does Le Chatelier's principle tell us we're going to do now? What are we going to do? If you remove something from a system in equilibrium, what happens? The system does what? It minimises the change by trying to put it back. So I remove that. The system's going to try and put it back by favouring the forward reaction, which is the exothermic reaction. So it's always the exothermic. So if you take heat away, the system will respond by trying to put it back by favouring the exothermic direction. If you heat something up, okay, you're putting heat energy in, okay, it's going to try and absorb it, get rid of it. And the only way you can get rid of it is by absorbing it. So you're putting lots and lots of heat energy in, it's going to try and take it out by absorbing it. And so heating something favours the endothermic direction. Should we write that down? So really, I should talk in terms of increasing the temperature, shouldn't I? Because we're talking about the effective temperature. So if we're increasing the temperature, we're adding heat energy. The system's going to respond by trying to minimise that change by removing it. And the only way it can do that is by favouring the endothermic direction, which absorbs that heat energy to remove it. Okay? That's our starting point. So if you heat a system, you favour the endothermic direction, because it will try and absorb that added heat. If you cool the system down, that favours the exothermic direction, which puts the heat back. If I was to put that there. So look at this value, and that tells you what the forward reaction is. The moment you see that, write in exothermic, and pencil endothermic. And we're cooling this down. Now, this is a really critical point, which is why I want to finish this. What's happened then is you've caused both of these concentrations to go down and this to go up. Now, the relative concentrations of these haven't changed. Okay, you've not added anything in. And so if these are both going down and this is going up, it's telling you that Kc is changing. In fact, Kc is the ratio of products to reactants. And so if this is going up and those two are going down, then Kc must be going up. Okay? So I won't go and put that absolute value up, but what I would say, and this is where we can finish, because it's a really good place to finish, and we'll do lots of examples next lesson, is heating and cooling causes the value of Kc to change. Okay? And that is a big take-home message. So remember, changes in concentration and pressure do not affect the value of Kc at all. It remains unchanged. Heating does cause Kc to change. They often ask you about this.
So in this, in what you just wrote here, Kc increases?
Yes, because since Kc is the products over reactants, it must increase. But with the others, what you're doing is you're imbalancing either the product concentrations or the reactant ones. The pressure one's actually a quite subtle one, but you still are imbalancing them. Here, you aren't. You're just increasing the reactants or the products relative to the reactants. So you're changing Kc up or down. So can I write that down, say here, very quickly? And that is really, really important. Put it in green to distinguish it from the other two, where changes do not cause Kc to change. If you were to take a reaction system and heat it or cool it, what effect would that have on the value of Kc? They often throw in a sort of sideways question where they've asked you about pressure changes or concentration changes and say what will be the effect of this on the value of Kc at the end. They just throw it in as an after effect because people won't be thinking by that point, oh, well, it'll increase. Remember, it doesn't change for pressure or concentration changes. Kc only ever changes if you change temperature. Okay, so let's have a look at an example where we know something about which direction is exothermic and endothermic, but we have to predict what would happen to the value of Kc if you were to heat it or cool it. So we'll do that now, okay? We're going to heat it or cool it?
Cool.
You want to cool it?
Yeah. We cooled it last time.
So if we cooled it last time, should we warm it up this time?
Yeah.
Okay. Okay, so we're going to look at this reaction. First thing to say is I have no idea what delta H is for this, so I've just made up a number. The important thing though is what? What does that tell us? Something about that.
Exothermic.
What is?
The reaction.
Which reaction?
Forward.
Okay, so if we look at this, it's good. More than one person tried to answer it. If we look at this value, we've got a negative value, and that's telling us that the forward reaction is exothermic. So that means the reverse reaction is endothermic. That's the moment you're asked anything about a change in temperature, look at that value and write in pencil that. Okay? You've got to work out which direction the exothermic and endothermic reactions lie. Don't assume it's always going to be exothermic forwards, endothermic reverse. Okay? Depends on which reaction you're looking at. Often, sometimes, they may even throw you another curveball by changing that the other way round and then just putting plus there. Because you can do that, as you'll see when you get to year 13, when you do something called Hess's law. If you change a reaction round, so that the products are now the reactants and the reactants are now the products, you just basically change the sign here. Okay? So this is our question. What is the effect on the value of Kc if the above reactions warmed up? This is a very straightforward question if you just follow the structure I said before when you answer one of these questions. So we're talking about equilibrium and the effect on equilibrium of heating. What's the very first thing we need to state in our answer? What is the change? Exactly right. So let's state what the change is. What do I need to do next? I've said what the change is. This is the thing that's going to cause anything that happens to happen. And the cause and effect. This is the cause. What's the next thing we need to put into our answer?
We improve the principle.
Yes, we start using Le Chatelier's principle, which says what?
Minimize the effect
Of the
change.
change. So we've warmed it up. It's going to minimise the effect of that change by trying to cool it back down. Yeah? How's it going to do that? If it's going to cool it down, it's going to be something to do with exothermic and endothermic. Which of those reactions cool down? Endothermic. So it's going to favour the endothermic direction, because you've warmed it up, it's going to try and cool it down. Yeah? So it's going to favour the endothermic direction. Remember when I say endothermic favouring a direction, it means that direction's going to go at a faster rate than that one. So in other words, what's on this side is going to go down in concentration, and what's on this side is going to go up, because they're no longer matching. Yeah? Is everybody still with me on this? Good, because this is the hard bit. Okay, the hard one. Okay, so let's apply Le Chatelier's principle. The system. So it's trying to minimise it. You've added in heat. It's going to try and take it away. So it does so by favouring the reverse endothermic reaction. So what's happening to equilibrium? You're favouring the reverse reaction. It's going to shift, isn't it? Which way? Do we use the word left? Okay, so equilibrium shifts to the reactants. Never use left or right. Okay. What that actually means then is the concentration of reactants is going to go up, whereas the concentration of products is going to go down. So why don't we write that down? That hasn't answered the question yet, and I'm saying that because often you'll find with a question like this, okay, a student will go through all of the explanation as to what happens because they're so used to just applying Le Chatelier's principle, they get thrown in a part of a question which they don't usually answer. So they don't answer it. So this hasn't answered the question yet. It's got you in the position where you can answer the question. So we need to look at what the effect is on the value of Kc. What's Kc equal to? How do we work it out in terms of a very generalised way? How do we work out the value of Kc?
Product divided by reactant.
Exactly right, because that's what we've been given here. This is what we've just written. It's the concentration of products divided by the reactants. Yes? So why don't we write that down? What we're doing is we are increasing the concentration of reactants. The denominator is going up. The product concentration is going down. So the numerator is going down. This is going up. That's going down. What's happening to the overall value of Kc? It's actually getting smaller, isn't it? Yeah, well done. Okay, so why don't we write that? So all of this explanation using Le Chatelier's principle is just to get to this point where we know what's happened to the concentration of products and the concentration of reactants. Then we can just plug in the general trend and that'll tell us what's happened to Kc. And that is probably about the hardest question that can be asked for equilibrium. What I want to do is just move on to the very final thing, and that's catalysts. And it's very straightforward. What is the effect of adding a catalyst to a system that's in equilibrium? And the answer is very, very simple. A catalyst, what is a catalyst? Tell me, what is a catalyst? It lowers the activation energy barrier, but what does it actually do? Yeah, it does that, but what's actually the effect of that then? It speeds up a reaction rate. And there's one other thing that you need to add in with that. A catalyst is a substance that speeds up a reaction rate, but it's not used in action. That's actually very important because it tells you it's not a reactant or a product. It's just helping the reaction along in some way. Okay? So the catalyst speeds up a reaction rate. The thing is that with a reversible reaction, it actually speeds up the forward reaction rate at the same amount, by the same amount as it does the reverse reaction rate. Okay? So overall, it doesn't affect the position of equilibrium at all. Okay? So adding a catalyst in doesn't affect equilibrium or the position of equilibrium. What it does do, though, is it speeds both reaction rates up, so you get to equilibrium faster. It's the same place, but it's there faster. Does that make sense? Very simple, just a couple of sentences to write it. They might ask you something. It's very rarely asked, but it might be asked, so it's a good idea to cover it. So 3 things in there that are important. They do not affect the position of equilibrium. The value of Kc is unaltered. And the system reaches equilibrium more quickly. So that's the only difference using a catalyst does. So in industry they are still used. So this reaction is a real reaction that's used in industry. They do use catalysts because they get to the equilibrium faster. And time's money.